Welcome to homework.
One of the ideas for space propulsion is the so-called solar sail. This solar sail makes use of the fact that electromagnetic radiation in light and other forms carries energy and momentum, and therefore can create a pressure on a surface. This pressure, which I'll write as a curly big P, is related to the intensity of the light or radiation divided by the speed of light, c. And if the light does not bounce back, you have complete absorption. And this is the pressure that I'm writing down for an absorber. But your pressure is different because your momentum change is twice as much if the light or electromagnetic wave is free to reflect from the surface. And of course, something in between could actually happen. But here we're going to assume that our solar sail uses the greatest pressure. So we're going to go with the reflector. And most visualizations you see of the solar sail has a great big sort of milerized sail coming off of it. Anyway, what we're doing with this is we're going to be using Newton's second law in order to figure out how to propel this spacecraft. So the problem is there is a force of gravity pulling the craft towards the sun, and we'll make this a 10,000 kilogram craft. And we would like the radiation force, we'll call that F rad, to be at least as big as the gravitational force. If it isn't, that spacecraft isn't going anywhere. So it's got to be at least equal to the gravitational force. And that's the situation we'll look at. Is we'll set it equal for now and just see how large of a sail it takes for this to keep from being dragged into the sun. Okay, so the force of radiation is the pressure times the area of the sail. And I'm going to put a subscript on that because there is another area involved. And that has got to equal Newton's universal law of gravity, which involves big G, the mass of the sun. I'll write that down as 1.99 times 10 to the 30th kilograms. And little m is our spacecraft mass. And that's all divided by the distance squared between the sun and the craft. Okay, now let's work with the pressure. The pressure is twice the intensity. And the intensity drops off as 1 over the square distance from the sun. So we're going to see something interesting happen. The intensity is the power in the radiation, and I need a different P. We're getting lots of different P's, so let me write that as delta E maybe. No. There aren't enough letters in the English alphabet for all the things we want to represent. I'll give it a big, bold-looking bottom to it, power. So the intensity is power divided by the surface area into which the body is radiating. So what we mean here is our sun is radiating completely all the way around into spherical surfaces. And one of those surface areas at a distance d from the sun is 4 pi d squared. Okay, so we see that the intensity actually drops off as the distance squared as well as the gravitational force. Okay, so putting this together, we have twice the power, the big P, over 4 pi d squared, and then there's the speed of light in there. Okay, so we're putting in the intensity times the area of the sail is g, mass of the sun, mass of the spacecraft, over d squared. So interestingly enough, the size of the sail is going to be impervious to how far the spacecraft is, which is probably why this looks like a good idea to many spacecraft people. So let's solve that for the area of the sail. It'll involve some constants and some masses. Speed of light and the power emanating from the sun. The power, by the way, we know is a full 3.9 times 10 to the 26 watts. And we know the mass of the sun as well, which I believe I've written down. Yes. So putting this all together, I don't know if you'd like to see all these numbers, but we wind up with the area of the sail. I'll just show the final result. 6.37 times 10 to the 6 square meters, which most of us don't have much of a feel for. So it's probably good to imagine that it's a square sail, the same on both sides, with a length of a side A, and we can solve then for A as the square root of this area. And that turns out to be 2.5 roughly times 10 to the third meters. And that we can easily visualize. That's about 2.5 kilometers. So our sail area is going to be 2.5 kilometers by 2.5 kilometers. And that is the size of a small city. The city in which I live is maybe just a little bit larger than that. So it shows that the sail size is going to have to be appreciable. No small feat. Of course, the other thing you could do is have a smaller mass in your spacecraft. So make your mass smaller and your area won't be as necessarily large.